Let's talk about section 3.2, measures of dispersion. It is also nice for us to have numeric descriptors that tell us the shape of the distribution of the data. These values are called measures of dispersion or variation. There are three types that we will discuss in this class: the range, variance, and the standard deviation. The easiest measure of dispersion to calculate is what we call the range. The range is a measure of dispersion that is the difference between the largest and smallest values in the data set. So the range is a very easy formula. We take the largest value given in the data set and we subtract the smallest value given in the data set. Let's look at an example. The following data were collected from a sample of call lengths in minutes observed for two different mobile phone users. Calculate the range of the data set. So we have 2, 25, 31, all representing minutes, the lengths in minutes of calls here, okay? Now, this is not a very large data set, but there's still enough to where we may make a mistake. So traditionally, I like to do what we did with the mode and organize our data set from smallest value to largest value. Now, since this one is not very large, we can easily see that 44 is the largest data value and 2 is the smallest data value. So our range is 44 minus 2, which gives us 42 minutes. The most commonly used measures of dispersion are variance and standard deviation. Both are used to measure how far the data values are spread out from the mean. A larger variance or standard deviation indicates that the data is more spread out from the mean, while a smaller variance or standard deviation indicates the data is less spread out and therefore lies closer to the mean. So a larger standard deviation means the data is going to be more distributed away from the middle. Remember, the mean is the middle. Whereas a smaller standard deviation, the data is going to be distributed closer to the middle of the distribution of the data set. Variance and standard deviation are closely related. In fact, variance is the square of the standard deviation. So if you know one value of a data set, then you can easily obtain the other using simple arithmetic and, of course, your calculator. The sample variance is a measure of how far the data values are spread out from the mean. Variance is a squared measurement. So we denote variance by the letter S, and it's the square of the standard deviation. So notice we're setting ourselves up for our notation for standard deviation. We use S because standard deviation starts with S. And since variance is the square, we write the variance as S squared. And we can go into this formula, but again, our calculator is going to be very useful here. So we're not going to utilize this formula. Your formula sheet does have this formula on it, but it's going to be easier if we remember using these techniques for our calculator, how to do it very quickly and easily. The sample standard deviation is a measure of how much we might expect a typical number of the data set to differ from the mean. So again, if this is S squared, to get S, we will square root it. So the formula looks very similar. It's just the square root of what we had before, and now S squared just turns into S. And again, we use S for standard deviation. Okay, let's look at an example. Calculate the sample standard deviation and sample variance of the given data set. So here are our data values. There's 1, 2, 3, 4, 5, 6, 7, 8 data values. I always like to keep that in mind when I'm plugging them into my calculator to make sure I didn't miss a data value and ruin my answer. So again, even though we have a formula to do so, we will calculate the standard deviation and variance using our graphing calculator or our smartphone app. Doing so is faster and much easier. So again, we're going to utilize our stat button. This is a very nice button for this chapter. Our stat button, and then we're going to click edit so that we can edit our columns here. We're going to put all of our data, 2, 1.7, so forth, given in the previous slide, into our column L1. Once we've done that, we click second and mode, and this will take us back to the home screen where we're able to calculate our statistics. So again, we're going to click stat and then highlight our calc and click our 1var stats. This pulls up our 1var stats function. And we're not using any weights here, so I only need to account for L1. So I'm going to click second and the number 1 and then close off my command using a right parenthesis. Now, we could look at the mean. This is what we did in the last section, but we're going to be more interested in our SX value here. This is the standard deviation of our X values. This is how your calculator denotes it. And we see that it's equal to 0.47037219,306. And again, the book and homework will tell you how to round these values when they want them. Our variance is the square of our standard deviation. We can calculate this by scrolling down and squaring our value Sx on our calculator. Now, the book involves a rounding rule where it says to round to a certain number of decimals. I always like to use 6 decimals because this guarantees later on when we're in our future chapters that we're not making an error in our calculation. This is one math class where our calculations are extremely important and we don't want to have any error using decimal numbers. So I always like to tell students, and I personally prefer to always use 6 decimals when writing down a decimal number, and then at the very end of the problem, rounding to the appropriate number of decimals. But the book does this section slightly different. If you want to follow their techniques, that is okay too. Okay? So we saw that our standard deviation was 0.47. I'm going to use 6 of these decimals. So I take 0.470372 and I'm going to square it, and I see that my sample variance is 0.221249,8, so forth. Up to this point, we have only discussed numerical descriptors of a set of sampled data. Remember from section 1.1, these are called statistics. What if, however, we wanted numerical descriptors of a set of population data? Remember again from section 1.1 that these values are called parameters. We distinguish between statistics and parameters with our notation. We have already seen the following statistics. Our sample mean. Remember, this was given in the last section by X bar. And we also had our weighted mean, which I'm not going to put up here. And then we have our sample standard deviation, and this was denoted by S. And our sample variance, which is denoted by S squared. Our corresponding parameters, remember parameters correspond to population. They both start with P. Will be labeled using the lowercase Greek letters mu, which is kind of like a U with a little tail in the front, and the lowercase letter sigma, and this is like a cursive O almost. Here. And mu, we use mu because it starts with M, and so that's going to represent our mean. However, it's going to represent our population mean. So mu is our population mean. Sigma, you guessed it, it starts with an S, so it's going to represent our standard deviation. However, it's going to be our population standard deviation. So sigma is our population standard deviation. And then to find our variance, remember all we do is square our standard deviation. So sigma squared is our population variance. Now, we do have formulas for all of these. They're slightly different. The mean is the same. We just use capital N to represent our population instead of lowercase n, which represents the size of our sample. But our sigma squared and sigma are slightly different. Notice we don't subtract the 1 in the denominator. But again, if we need to calculate these, our calculator will do it for us. Our graphing calculator will calculate all of these values, as I have just said. In our output, mu is the same value as our mean. So if we want to find mu is actually x bar. They're calculated exactly the same. Sigma, however, instead of looking at Sx, we go down right below it and we see sigma x. This is our population standard deviation. And remember, to find sigma squared, all we do is take sigma and square it. And again, personal preference, I always like to use 6 decimal places to make sure that I don't have any error in my calculation. We can use the standard deviation to help us determine how spread out the data values are in relation to the mean. Let's now turn our attention to the bell-shaped distribution of data shown here. Right? So we've all probably seen a classical bell-shaped curve. Notice that in this case, the mean, median, and mode are all equal, and the distribution is symmetric about its center. So this middle point that gets the highest point on the bell is where our mean, median, and mode all lie. So if we imagine this as a number line, all of our data is spread out along this number line, and the mean, median, and mode are going to be this value on the number line. Okay? Now, what's going to happen is our standard deviation is going to either stretch this graph out or squish this graph in. So it's going to be very elongated if we have a larger standard deviation and very flat. Or if we have a smaller standard deviation, we're going to squish it in. So it's going to be really short, and that's going to create a higher peak here. Okay, and we'll talk more about this in chapter 6. Now, with bell-shaped distributions, we have what's called the empirical rule. The empirical rule can be used to estimate the percentage of values within a few standard deviations of the mean. Instead of reading this, let's look at a visual. I always like to put these statements to a picture. So the empirical rule says the following. If we find the mean for our bell-shaped distribution, remember the mean corresponds to where the highest point is. So here's our mean. And then if we start moving one standard deviation to the right and one standard deviation to the left, the empirical rule says that 68% of the data values are going to fall in this portion of the number line. If we move 2 standard deviations to the right and left, then we see that 95% of the data is going to fall in this portion of the number line. And then if we finally move 3 standard deviations to the right and to the left, 99.7% of the data values are going to lie in this portion of our number line. Let's look at an example. The distribution of newborn babies in one region is bell-shaped. So this gives us a hint that we may use the empirical rule, because now we have a bell-shaped distribution of data. And they give us the mean. So with a mean of 3,000 grams, and they give us the standard deviation, 500 grams. So we can start filling in this table. We have a mean of 3,000. So I would mark this on my line as 3,000, and then our standard deviation is 500. So this going up 1 standard deviation would give us 3,500, and then 4,000, 4,500, Going down would give us 2,500, 2,000, and 1,500. Now we want to find the percentage of newborn babies that weigh between 2,000 and 4,000 grams. Visually, remember 2,000 was here, and 3,500, 4,000 was here. So we're between two standard deviations. I always like to draw a picture. So 95% of the data should be there. Mathematically, we can calculate it as follows. First, we find the distance. So if our first value we're looking at is 2,000, then the distance from the mean is 2,000 minus 3,000, which gives us negative 1,000. That tells us that we're 1,000 units to the left. Whenever we're negative, we're to the left of the mean. And if we look at 4,000, we're again 1,000 units away from the mean, but now it's positive, so we're positive 1,000 units away, so we're going to the right of the mean. So this tells us that 2,000 is 1,000 units to the left, and 4,000 is 1,000 units to the right of the mean. Now, to finish this problem, we divide by our standard deviation. So we take our distance divided by standard deviation, and we see that our distance divided by standard deviation is -2, and for the value 4,000, it's +2. So we're between two standard deviations to the right and two standard deviations to the left, which is exactly what we saw when we drew this picture. We went 4,000 was here, 2,000 was here. So we're within two standard deviations. So that tells us 95% of newborn babies weigh between 2,000 and 4,000 grams. Okay, let's look at our last example. The distribution, again, of newborn babies in one region is bell-shaped, so we have the same setup with our mean 3,000 and our standard deviation 500. What percentage of newborn babies weigh less than 3,500 grams? Again, we can look at our picture. 3,500 was 1 unit to the right, but now we want everything below because we want to be less than 3,500. So we have to do a little thinking for this problem here. How do we use this picture to get all of this data? Okay, so again, we first determine the distance. So if we look at our value 3,500, the distance from the mean is 500. So we saw in our picture, we went 1 standard deviation to the right of the mean. That's what this tells us here. The number of standard deviations is 1, right? That we saw this again from the picture. So here's our picture we're looking at. We have our mean at 3,000. We're 1 standard deviation away, and we want all of these data values. Well, we know that the middle cuts it in half because it's symmetric. So we know that half of this contains 50% of the data, and half of this contains the other 50%. So we already know that everything below 3,000 gives us 50% of the data. We can use our symmetry here. Notice when we're between 1 standard deviation to the right and left, 68% of the data lie here. Because of our symmetry, that tells us 34% is here and 34% is here. So if we add these two percentages, we see that 84% of the newborn babies weigh less than 3,500 grams. Now, a fun exercise. We've gone through a couple things in this section already. Find the range, sample standard deviation, and sample variance of this data set. Try this using your calculator. The one thing is your calculator will not calculate your range, so you have to remember that it's the largest minus the smallest data value, which is very easy to remember. If you have any questions on this, please reach out to me, email, or post on our discussion board. And then finally, try doing this problem with our empirical rule. So suppose that private school tuitions in one region of the country have a bell-shaped distribution. So they're telling us, hey, this is bell-shaped, here's my mean, and here's my standard deviation. And we want the percentage of tuitions that are between these two values. So give that a try, and if you're struggling with this before attempting the Hawks homework, send me an email.